So here we begin with our Unit 4 first lecture, and we're dealing with the first type of bonding. And this is not the first time we've dealt with bonding. In fact, I told you way back when, you could color your choice. Okay, I left the red and black.
Red and black.
Yeah.
Hey, Lily, you got me a new one. This one's
People have to have their right colors. But we left off talking about ionic bonding. All right, and ionic bonding is a type of bonding where atoms use each other to do something. Yes, Sam? K and who? All right, so K and Cl. So let's think about this for a second. Now that we have our whiteboards, we're ready to rock and roll, and I'll tell you what we're going to do in a second. I need your focus up here. Ionic bonding, from your last test, which I'll probably go review tomorrow with you. Okay, I asked you who would undergo ionic bonding. And you guys now know that I take a metal who becomes positive, and I would take a non-metal who becomes negative, and that would create opposite ions, and they would attract each other. Okay, well, let's look a little closer.
Wouldn't two of the same elements share?
Yeah, and that's the next type of bonding, is sharing those electrons. But the whole idea today is understanding this. Bonding is about elements getting stable. And stable is what kind of energy? High or low? Mr. Stable dropped to the floor. He didn't have much energy. Mr. Unstable, I'm not sure how you characterize Mr. Unstable. Maybe you'll look at me differently after I've done that. Okay, there's a little twitch in my eye. That guy is not going to be in a room by himself. The point being is Mr. Unstable had too much energy. So atoms, things in nature, physical science. The whole idea here is that things go from high energy, usually to low energy. It's a thermodynamic pathway. A rock on top of the hill goes to the bottom. So when things bond, and you have to understand this, the first most important skill here, or the first skill, is that when atoms do bond, they do so because they become stable. They want to become low energy. When you go and you get to the end of the day, do you do wind sprints? So at the end of the day, when you're done doing all your chores and your homework and Mr. Grodsky's long lectures, do you sprint? Okay, do suicides, as they used to call those? Do you? No, you what? You relax. You chill. Or some people say, chillax. You get stable. You put your feet up. You might text your heart away or whatever you might do at night. But you get comfortable. You eventually fall asleep. You eventually get low energy. Atoms want to do the same thing. But they do so by using each other's electrons. This is the first type of bonding. Now, getting stable means that they both get lower in energy. Now, how do elements get lower in energy? What do they do with their configurations? Who has the lowest energy of all the elements? Who has the lowest energy of all the elements? What family, as I'm pointing to right here, has the most stable electron configurations? The noble gases. These noble gases have the lowest energy. They're already, guess what? On the couch. Why? What's so special about noble gases? Yes, Karen. They have a stable electron state, or we can say they have a stable low energy electron configuration. What is the most desired electron configuration? One in which the electrons in the orbitals are filled or unfilled? Filled. When they're all filled, you are stable. That's why we saw the graphs spiking up and spiking down. So, when bonds are made, energy drops. That's it. Atoms use each other to try to become like this. And there's two basic ways. There's a transfer and there's a sharing. The sharing is called covalent, which we'll talk about a little bit later. Ionic is the first way because it's the way that I introduced you to already. So take, for instance, let's look right here for a second. Let's take potassium. Let's do sodium. Look at sodium right here, Na. Okay? And let's white this out, because I can. Now when I white this out, it'll be all white. But the point I'm trying to make here is that sodium has this configuration. All right, so sodium, Na. Now, it is 2-8-1. Now, you all know that these electrons, what's the maximum electrons that can fill the first energy level? 2. That's stable. Who has electron configuration of 2? Helium does. All right? And then 8 fills the second maximally. This is a ground state configuration. And then there's one more. What do we call this outermost electron? Valence. But what's so special about valence? Because we're going to be dealing exclusively with valence electrons now. What's so special about valence electrons? Well, they're used for bonding. They're the electrons that get involved so that this guy can get stable. My friends in chemistry, sodium is so unstable, you throw it in water, it explodes. I've shown you that, and we'll do it live. Not today. All right, but sodium is unstable. But we have sodium everywhere in our environment, but we don't have sodium 0. Now, how can it get stable? Well, let's throw some chlorine into the mix here. All right, let's throw some chlorine. Now, if I look to the right, where my nonmetals are, I can find my chlorine is right here. It's above that staircase. And its configuration is 2-8-7. How many valence electrons does it have? 7. It's in group 17. So my friends in chemistry, notice I took an element that was a metal, and I have a nonmetal. Now, this is important. Sodium, it could gain 7 to have the same electron configuration as whom? It could gain 7 and have the same configuration as argon.
But isn't it easier to lose?
But as you just said, it's easier to lose one. Yes, Kara? Yes.
It'll be easier for chlorine.
And it's easier for chlorine to gain one to become like. Now, I say become like, not become them. We're not gaining and losing protons. What makes atoms different is the atomic number. So they become like. And that like that we're talking about is low energy. So guess what? Chlorine needs one to become stable. Sodium could lose one to become as stable as neon, argon. So look at here. All sodium has to do, all right, all sodium has to do is lose this one, and if it could, it would become 2-8, which, by the way, is the same configuration as neon. Chlorine, if it could gain one, would be 2-8, and it would have the same configuration as argon. Both noble gases that have filled energy, let's just say they have filled orbitals, okay? And they're very stable. Now, how can this work? Because it clearly, that's the easiest pathway. Well, my friends in chemistry, here's how it can easily work. Sodium's a metal. What kind of ionization energy does it have? It's big. It's a big radius. Electrons are farther away from the nucleus. So it has low attraction, low ionization energy. This can lose an electron to do this because it holds on to them loosely because they're bigger radii. The nonmetals, as we go across and the nuclear charge increases, we pull in the electrons, and this guy right here, chlorine, I'm not pointing to him, but chlorine loves to gain electrons. What do I say? It attracts its own electrons and it fantasizes about gaining some more. And this can become -1 because of that. So these guys, not only can easily achieve these stability issues, they have the ability to do so because this is a big fat radius, and this is a what? This is a small radius. Nonmetals gain, metals lose. So when I put this pair together, this is what I want you to write. I want you to write sodium 2-8-1, chlorine 2-8-7. I want you to write it just like I did. All right? Now, let's draw something called a Lewis dot diagram. Lewis dot diagrams are diagrams that show how the bonding has occurred or does occur. Okay? Again, we're after stable electron configurations. So my friends in chemistry, here's what I do. Let's white this out in the bottom, give myself some room. And here's my sodium. Sodium, oops, I don't want to do that big. Sodium has one valence electron. So I draw one dot. The Lewis dot diagram of this element represents the valence electron and its symbol. The symbol represents the core electrons and the protons and the neutrons. I'll say that again. The Lewis dot diagram, the dot represents the valence electron that's involved in trying to get stable, and the rest of the electrons and the core electrons and the proton and neutrons represent the symbol. Okay, there's one big dot there. I'm not sure what, there's a little dot there. Okay, oh, that's what that is. And now chlorine, the nonmetal. Chlorine. Well, my friends, in chemistry, chlorine has 7 valence electrons, so I draw 7 dots. Each dot represents the valence electron. We've covered this. Dot diagrams, the dots of the valence. All right? Now, you're going to hear this word a lot called the octet rule. The octet rule means to become stable, with the exception of hydrogen, who wants 2 electrons in its first energy level, everything else we deal with wants to have that magic 8. This is going to get to an 8 if it can lose 1. This can get to the 8 if it gains 1. Right. So, here's our scenario. These guys come together, right? Right now. And what do? Bond! Okay? Now, why do they bond? Because there's a great little song, a little screamo in there, a little sensitive to screamo. What happened is this, party people, this guy easily loses. This guy easily gains. This is a great pairing. What kind of electronegativity does sodium have, you think? Electronegativity does sodium have? It's a metal. It holds on to electrons. What's electronegativity? It's a fancy word for electronegativity. Attractions. Put pinky up. It's a fancy word for attractions. So when I look for sodium, Na, and I look for its electronegativity, I see that it's what? 0.9. Sodium's electronegativity is 0.9. Where am I looking, guys? Table S. Now you should know, anywhere to the left and down where atoms get bigger, their attraction for what? Electrons is low. It increases, that's the graph you did, and boom, it starts again, right? It increases, boom, it's low. It increases, boom, it's low. Okay, remember that graph you guys did? So guess what? So we have 0.9, very low attraction. Who is my other counterpart? Chlorine. Of course, it's a nonmetal. Look, its attraction is what? 3.2 high. We're going to write those above our elements right now. Okay, so put the 0.9 and 3.2 above that. So I'm going to do the same thing. So above my sodium, I'm going to write 0.9 and then 3.2. Okay, bad planning on my part. But I can move stuff around because I'm tall. Maybe. Probably should have did this. Okay? And I'll move the other guy around too, because I can. Oh, yeah, don't do that. One more time. Maybe not. Okay, so we get the idea. Now, I got 0.9 and 3.2. Clearly, guys, this has a high attraction for electrons. This has a low attraction. You need to visualize it. Where's our friend at? Where's Elvira, the outermost electron? Okay, we got sodium. Okay, sodium's got its electron. Okay. Sodium. Then we got who? Chlorine. Elvira, the outermost electron, is what? Pulled tightly. I attract electrons, and I'm wanting more. Whereas you got sodium. Whatever. Well, it's kind of like, well, I don't have much attraction. So, what's going to happen? Who wants to come up here with me? Tug of war. I won't hurt you. Come on, Kara. Kara's going to be the metal. So is she going to win or lose? Right. So it's all rigged. Kara going to stand here. He's going to represent sodium. This represents your valence electron that's held so far away from you. Hold this. Yep. Stand over here facing me. Okay. Now, hold up. Come back, come back.
Back.
Yep, to me. Come to me, come to me.
A little bit more.
All right, yeah. So I'm chlorine. Who's stronger for electrons? This is her outermost electron. Notice it's held far away from her. My electrons are here. So we come in contact. I have a high attraction. She's got an electron. I want it. So there's a tug of war. Who's going to win this tug of war? I am. You have to lose. You're supposed to lose. Come on, give me that.
Now I'm losing?
Yeah, you're losing because I am what? More attracted. Whoa! I got stable. I got stable.
I had a rubber to my face.
No, listen, look. I'm happy. But listen, you're just as happy too. Why?
Because you want to.
Right, she got stable. I got stable too. I gained my electron, right? Rope art. It's going to catch on. All right, there it is. All right, I just got stable. Now, the thing is, though, you became what by losing electron? An ion. What kind of charge? You lost a negative that I have now. So what charge are you? I just became a what? Negative. So my friends in chemistry, now we bond. All right? And now we would bond electrostatically. She's negative. I'm sorry, I'm negative, she's positive, and the attraction we have for each other is now the ionic bond. Notice something. Did we share the rope? No. The rope was transferred. I pulled the rope away from her. Thank you, Kara. So just like that, watch what happens. This electron is yanked right to the chlorine. Maybe. So this electron goes right to the chlorine. So show that arrow. I'm having trouble doing so. Okay, go back. Point. Okay, so the arrow, this electron goes here. And what does it look like now? Well, here's what happens. Here's what I draw. This sodium loses this electron. Oops, can't do that. Let me go somewhere else. File new. So let's do this. So you should have this. You should have your sodium, who had one valence electron. You have your chlorine, who had 7. Chlorine being that much more electronegative. What was the number for chlorine? 3.2. Sodium was 0.9. The difference in electronegativity, the attraction for electrons, is so great that he yanks that electron away. So that electron goes and gets pulled away. So what you write is the following. You have to draw sodium with no electrons. That's Kara. And we say the entire piece of sodium is now +1. +1. I draw brackets. Brackets tell me the entire thing is +1. I show no electrons for the metals because the metals lose their valence electrons. Metals will always have nothing left. Chlorine, what does chlorine look like? It gained an electron.
All 8.
Right. It shows all of the 8. It started with 7. Right? And I'll just change the color. It gained 1 more. What charge is it? -1. And this is very important. The charges in your Lewis dot diagram to show the bonding will always be a net of 0. They have to always equal 0. This +1 equals -1. And this shows the bonding. Cara and I ionically bonded. The positive ion that resulted, losing electrons, became positive. The one that gained became negative. And this positive one is attracting this one. And we call this an ionic bond. This is an ionic bond. Notice the word ion in it. Everything you learned about the trends is coming to fruition here. This is an ionic bond. Now, how do I write the formula? Formula is easy. The metal goes first. Metal goes first. So we have sodium, and we write the nonmetal second, NaCl. And we also write something else. We write the phase. It's solid. Ionic compounds, which are from a metal and a nonmetal, from someone who loses to someone who gains. So it goes from a metal and a nonmetal. Always result in ionic compounds. Because if you've got a metal whose big fat radius and holds onto them loosely with a low electronegativity, it'll lose the electron easily in the tug of war to the one that's stronger for electrons, that gains electrons. And the difference in the ions creates the attraction called an ionic bond. Now, how do we name this? Easy. We name the one in front, which is always positive. We call that the element. So this is sodium. So we write sodium. And if you don't know the name, table S tells you. And the ending. Well, this is chlorine, right? So you start with chlorine, but this is important. It ends in IDE. It is chlorine, but when you have ionic compounds that are binary, that means two different, it has an IDE ending. This is called sodium chloride. It is table salt. Now wait a minute, we've all had table salt. It's made of sodium and chlorine. Sodium explodes in water, I said, was unstable by itself. Chlorine is a toxic gas by itself. When I have table salt in my french fries, it doesn't explode and I don't die from poisonous gas. What's happening? When the elements bond, what happens to the properties? They become stable, which means become low energy. You can jump on salt, you can pet salt, you can have a party with sodium ions. I wouldn't have a party with sodium metal. Difference, right? Unstable. What's the configuration of sodium metal? Remember? We just had it. It was 2-8-1. This 1 was 1 away from being stable. What's the configuration of sodium now? Plus 2-8. What's the configuration of chlorine? It was 2-8-7. Now it's 2-8-8. My friends, they both became ions to satisfy the octet rule and became as stable as a noble gas. When we put sodium chloride in our mouth doesn't explode. We don't die of poisonous gas. And we learned in September, when atoms bond, they achieve what? A whole new set of properties. Okay? So, what's an ionic bond? When you have what two types of elements? Why? Why must the metal and non-metal make an ionic bond? Because it's the why is the important part.
Because one has to be positive ion and one's negative.
Right. You have to become positive by losing. You have to become negative by gaining. So if you put two elements close together, where one is good at losing, one is gaining, electrons, and this is the key word, write this. Electrons are transferred. So in ionic bonds, what do we have? We have a transfer of electrons. You should know why, not just, if I can spell, transfer. Well, I can do this. Of electrons. Okay, why? Because you're going from someone who loves to lose to someone who loves to gain. All right. Let's try this. Let's take sodium. Let's take lithium. Let's do sodium again. Sodium and fluorine, or as they say in England, fluorine. I want you to do this. Write me the Lewis dot diagram for sodium and fluorine bonding. I'll give you hints, ionic bonding. I want the chemical formula and the chemical name. You can take a picture with your phone and erase.
This?
Yeah, absolutely.
After we
But
take
you
a
can
picture?
erase it?
Yeah, take a picture with your phone.
Of this?
Yeah, this is your notes, right? Take a screenshot. I mean, I have these notes printed for you, but it's nice to see your work. You can also take a computer out, your school-given computer, right, laptop, and you can take a screenshot that way too. There you go. All right, so Na and F, I want three things. Lewis dot diagram. I want the chemical formula and the chemical name of this salt. Hey, I just changed ionic compound to the word salt. Isn't sodium chloride salt? Guess what? The word salt means anything that's ionic. So we use table salt as the word for salt, but there are hundreds of salt compounds.
Can you put up periodic table again?
Absolutely. Periodic table coming up.
Are we erasing it? Yeah.
La la la.
Hi, add you.
Okay, so here we go. Make this smaller. So now we're dealing with sodium and chlorine. Fluorine, sorry. So we're writing sodium. And sometimes it's helpful to start this way. Okay, the electronegativities I looked up. Now, it's not necessary to do that, but I like to write them to show high and low. So I looked up electronegativity from table S. And there's a general rule with that. If the electronegativity difference is really, really high, then you know you have enough difference in strength to cause a transfer of electrons. For instance, in the last one, it was 3.2 and 0.9. And if you subtract those two together, you'll see that difference is greater than 1.7. It's called a 1.7 difference rule. You can't live and die by it. It's a general rule. Like this one right now, sodium is 0.9. Electronegativity, if you wanted to put that down, you don't have to, but it's kind of cool. This one is 4.0. It's the highest electronegative element we have. So here I have listed the electronegativity values. What is 4 minus 4.9? Yeah, so 4.0, which is the electronegativity of fluorine, minus 0.9, you get 3.1. That difference is pretty high. How do you compare it? It's called a 1.7 rule. If the difference in electronegativity is about 1.7 or higher, the difference in strength is so great, you can what? Pull the rope away. Okay? Well, this should look a lot like what we had before, right? What's going to happen, party people? Well, this electron is going to get yanked to the fluorine. And what you have is the Na loses its valence electrons, like all metals do. Becomes positive. Now, I write brackets. You don't have to write brackets, but it's a good idea. It's like being in church or temple. It's not polite to fart or give off gas, but it's not a sin. The reason why we have brackets is to show that this entire thing is positive. Let me show you something. The fluorine, all right, is going to have how many dots? Yep, once it's done gaining an electron, which nonmetals love to do, it has 8. And I draw another bracket. Now the bracket tells me that these electrons are not being shared. And there it is. So that's all you have to do for the Lewis dot diagrams. Go back to the other sheet and make it a little simpler. And what is NAF? Well, you're going to tell me in a second. You probably heard it before. Try to find the name. So here it goes. We have Na. Right. Anyone ever hear of sodium fluoride?
Oh, yeah.
Right, it's the active ingredient in toothpaste. Fluorine has its 8, started with what? 7 valence electrons. And it gains 1 more. And you show brackets to be polite. And the reason why you show brackets is to show that those electrons belong to fluorine. If you don't show brackets, guys, you may, important guys, if you do not show brackets, you may indicate in your illustration that these electrons are being shared. You want to show no sharing. There was a complete transfer. The fluorine gained the electron, okay, and became a -1. Very important. What's the formula of this? The formula is the positive one goes first, the negative one goes second. And we write solid because these ionic compounds make crystals.
Why is it 2?
I'm sorry, that should be solid. I'm talking but writing something incorrect. Thank you. That should be an F, and that should be an S for solid. And we're going to learn tomorrow that these things make ionic crystals. They are not molecules. They make solid crystal lattices. We'll talk about them tomorrow. These formulas we're having are the lowest ratio of ions. This is not a molecule. It is a crystal. And if you can think with me how crystals form, positives, negatives, are all tracking. Think with me for a second. If this thing is +1, is it +1 in one direction? Like the band?
That's what I thought.
I know. If I'm +1, any +1 in all directions? So that means the negative ion, which by the way is bigger. Why is the negative ion bigger? Because it gained an electron. Look what's happening. I can attract to the positive ion in what? All directions. And I'm building a what? A crystal. And then the negative ion can be attracted in what? All directions. That's why these things make crystals. Now, my friends, the formula of a crystal would have to be counting all of the what? Individual ions. We don't do that. We just find the lowest ratio. What's the name here? Sodium fluoride. Let's do one more. Take a screenshot. We'll do one more. So this is sodium fluoride. We can do it. All right, next, let's do calcium and chlorine. I'll help you out. What charge does calcium love to become? Well, we go to our periodic table. Calcium is an alkaline earth metal. Calcium. How many electrons does it want to lose to become stable? 2, right. So calcium has 2 valence electrons. And I said chlorine. Chlorine has how many valence electrons?
Oh, so would it be, I guess what the...
Little different. Calcium is what charge? +2. Chlorine's -1. Or calcium has 2 valence electrons, just like every single one of these. Chlorine has 7. Let's take a look at that.
Mr. Grosky?
Yep.
Would it be calcium and then chloride 2?
Absolutely correct. You're definitely seeing what I'm talking about here. So we got calcium, who has 2 valence electrons. Write it. Watch. Oops, don't write that. Calcium, 2 valence electrons. So calcium.
Is that why oxygen's O2?
Well,
Because they
almost,
share.
yeah. It shares to get there. So calcium has 2 valence. Chlorine has how many? 7 again. It just needs 1 more to become stable and have its octet. So what happens, party people? Well, the chlorine is going to gain 1, the nonmetal strong. So this chlorine has now 8. And it becomes what charge? -1. This calcium loses 1. But wait a minute. Calcium can't stay there as -1. It needs to lose another. So what does it need? It needs another chlorine, who has 7. Calcium can't stay there with 1 valence. It needs to lose all of its valence. So this loses another electron to another chlorine. So what we have here is this. Calcium, no valence electrons left, +2. It lost 2. How many chlorines are involved? The chlorines, one started with 7, and it gained 1 to become -1, right? And it needed a what? Another chlorine. So I didn't give it to you, but you have to figure out how many of each you need in order for all of the electrons to be transferred. And, important answer here, what's the overall charge? So this is CaCl2, calcium chloride. Okay, take your last screenshot. Okay, there's some homework. I'm going to post this lecture again if you're having problems. So just grab a sheet on the way out. The homework is to do the backside. Backside only. Backside only. Take your last screenshot. Please take one on the way out. On the way in. Sure, it's fine. Totally fine. The back side, the ones that the same thing we were doing, the back side drawing.
All right.
And I'm going to post the lecture. I have a key that shows you how it's done. You're welcome.